I think it's actually instead of backwards, it's shorter.
Let's get started.
This way. That's uphill. So I was thinking maybe it's like
Very good. All right, so these are the survivors. Talk about it more. I haven't looked at the exams yet. I've been out for the last 2 days myself. So, was it what you expected?
There was, I didn't have to use Gauss's law unless I did something wrong.
Yeah.
Like, there was no Gauss's law.
Yeah, it's true. That's not ornaments, not just true. But it was kind of like the homework, at least like.
Yeah. No, I think it was. I think so.
Time was the problem.
I did a lot of very silly mistakes. I wrote the charge induced by the
Yeah.
I'm glad.
We'll talk about it. I think we'll talk about it. We'll see. Oh, we'll get it back. But yeah. All right.
I took the exam.
We will see how it goes. Go from there. Okay. All right. So, but you know, the train doesn't stop. Keeps rolling. So we have another problem set coming, and we'll talk about it tomorrow. So let's sort of pick up where we were. We're going now beyond electromagnetostatics, and you know, so the new idea we have is this idea that beyond statics, if I look at a closed loop, I can have a situation where the closed loop of the electric field around a contour is not zero. It's zero in the case of electrostatics and magnetostatics, but it's not in more general terms. And the simplest case is when I put a battery across a resistor, I'm going to get a steady electric field inside that conductor, whereas we know in statics, the electric field inside a conductor is zero. And so we were talking about simple models that describe that. If I wanted to think about a material that had finite conductivity, had some resistance to it, then we can think about the Drude model, which is just a simple model of a free gas of electrons where there are defects that cause the resistance. So the electrons scatter off of defects at some rate that's called nu, and the equation of motion that describes the drift velocity of the electrons when a voltage is applied across the resistance, it's a very simple model. It's not a bad model, it's a pretty decent model of Ohm's law. It's not the familiar form of Ohm's law, but it is Ohm's law. And in steady state, we get that the current that is flowing through this resistor is proportional to the electric field, okay? You know, so that clearly is not just F equals ma, because it's saying the velocity is proportional to the force, right? Because the current is proportional to the velocity. This is a steady state solution to this motion with damping, okay? And the conductivity there is saying something about the density of the electrons. You know, this is the plasma frequency, as it's called. We won't talk about plasma physics in this course, but the plasma frequency is related to the density of electrons. The charge of the electron and the mass of the electron, okay? It's a property of the material density here, okay? And the other thing we talked about last lecture was the idea of ohmic heating. So because of these collisions, there is dissipation of energy, and the resistor will heat up. The work that you're doing to try to accelerate these electrons is being equally dissipated in steady state, so that there's a steady amount of energy in the system. And that is given by, as we showed last time, J dot E, okay? Right, okay, so that's some sort of basics there, just thinking about circuitry. And so the EMF in this case is coming from the battery. We said that the battery can give us a way of creating electromagnetic energy that drives the circuit through the chemical reactions that happen within the battery. But another way we can generate EMF is through the Faraday law of universal induction, okay? And what it says is that the EMF that arises from induction is equal to minus, or is proportional to, minus the rate of change of the flux of the magnetic field through the surface that is enclosed by this closed contour, okay? And loosely speaking, Faraday did the following. There are three equivalent ways we can imagine, say, the flux changing through this circuit. We can have it that we're pulling this, and this circuit is moving at a constant velocity v, in which case the flux through here is changing as I move that. And just from the Lorentz force law, we can calculate what this force is. So the EMF is the force per unit charge. And indeed, that is equal to, as we showed last time, the rate of change of the flux through the circuit with C in here, in these units. But, I mean, this was not the kind of way they thought back in 1830, whatever, when Faraday did this. We know that physics that happens should be independent of the inertial reference frame. Physics is the same in all inertial reference frames. So whatever is happening here should be the same as if I'm sitting on the circuit, and I will also see current flowing with a certain EMF. And so it's got to be the same whether the circuit is fixed and this, say, permanent magnet that is making this, imagine I have two permanent magnets that are very close to one another that makes this magnetic field, and I move the permanent magnets and keep the circuit fixed. I'm also going to generate the current because the physics is the same in all inertial reference frames. That kind of tells us that in this reference frame, since this circuit isn't moving, what is true is that there is an electric field. So this is the B field here, but in this frame, it's not moving. So the force, the Lorentz force, can only be due to an electric field. Okay? And so this must be equal to, we learn from this, although this wasn't until Einstein, no one really, it was really, if you read Einstein's original paper on relativity, this is the first thing he talks about. It's really good to read the original literature. It's fascinating. I mean, you learn this stuff filtered through Deutsch. What did I know? it's good to read the original literature sometimes, see what were they thinking? How did they get to these ideas? They weren't like Moses came down with the tablets and said there is, in the universal law of induction, there were thought processes that led to ideas. And it was thinking about Faraday's law where Einstein realized that there is something going on here that we have to think about how to transform between different reference frames because of this very fact. And there must be what is seen in the co-moving frame is an electric field. Okay. And this is equivalent to if I change this magnetic field in the same way as this motion, I get the same expression. And that's why we call it the universal law. It's not just about motional EMF. I can have both this nothing moving relative to one another, but have the magnetic field changing in exactly the same way as it would be changing here. How I would engineer that? No, but I'd have to make it shrink in the right way, but I would get exactly the same EMF. And all that matters is what the changing flux is. And what this tells us is that if everything is in the same reference frame as this is, that I can bring that derivative inside the integral, and the only thing that changes is the magnetic field, then I can use Stokes' theorem to say that this is also related to the local curl of the electric field, and the local curl of the electric field is generally given by the -1/c times dB/dt, okay? And as we said, the minus sign here is sometimes called Lenz's law, or Lenz's rule of thumb. Yeah?
What did you say the condition was for bringing the derivative inside the?
That this circuit is not moving. Okay. Otherwise, I have to think about how dl is changing with time.
Okay.
Yeah. So if everything's in the same reference frame, then we can do it that way. So anyway, what I was going to say is that Lenz's law tells us that the EMF is there opposes the changing flux. So what's happening here is as I move this, the current is imposed in such a way that it wants to increase the flux in a way that changes. Great. Okay. Very good. Now, that idea of back EMF, as it's sometimes called, work must be done to create an EMF. So the work I'm doing is I'm pulling this thing against the force that's going to be pulling in the opposite direction to oppose. I don't want my flux to change, is what it's saying. So it's got to pull in that direction in order to oppose that. And the work I do to create an EMF is energy stored in a magnetic field. So that was the last thing we talked about last lecture, is that if I have a current and I want to try to create a current, as I try to ramp up the current around the loop, I'm going to try to increase, that will increase the flux of the magnetic field through the loop. But that's going to create an electric field that's going to go in the opposite direction because of the minus sign, because of Lenz's law. it opposes, it's gonna make a current to try to make the flux not change. And I have to do work because now J, which goes in this direction, is minus E. So instead of ohmic heating, I have the creation of energy, right? Instead of work energy being dissipated, energy is being created by the work I'm doing. You know, energy's not for free. It comes for something, and there's work done by pushing the current against the back EMF. And that work, we can say, at the end of the day, is stored in potential energy. And that potential energy is stored in the magnetic field. And so what we get is that the energy density stored in the potential energy is this. Yeah, a couple of questions. First down.
Yeah, so we're going, talk about the back EMF and stuff like that based on Faraday's law. How much of a headache would it be to derive back EMF from Biot-Savart for increasing current in the loop?
Well, Biot-Savart doesn't tell us the whole story, because Biot-Savart is for magnetostatics. Okay. But the real story here is about this is the energy per unit volume per unit time from charges to field. So ohmic heating tells us how much work we've done on the charges. Minus J.E tells us how much work we're getting from the charges into the field. And so what we showed last lecture is we calculated this amount of the work we have to do, and that work is not coming from, in this case, the Biot-Savart, it's coming from the back EMF. It's the whole story. Yeah.
Why did you say J is in the counterclockwise direction again?
This is, I'm just saying this, we have some current, so that's the direction of J. That's the current, we have some current in this direction. That is the direction of the current. I'm not sure which, what.
Oh, but then you said, E is your.
E is the back EMF,
Okay.
right? And the back EMF arises from the change in current, right? Because the current is changing, if I try to ramp up the current, that's going to try to increase the flux. But as the flux increases this way, the back EMF is there to make the flux go the other way. Right? That's what that equation tells us with that minus sign. And so I have to, I can't just ramp up the current for free. As I'm ramping up the current, there's a force acting back on me through the back EMF, and I have to do work against that force. And that energy is somewhere, it's in the magnetic field.
What about the battery?
There is no battery here. I'm the guy pushing the current around.
Okay, so I thought you were the one supplying the energy.
I am. There is no battery. I mean, I could put a battery in here.
What I'm trying to reconcile is the fact that you're saying the energy is both inside the magnetic field and also it's being supplied by you.
I'm done. After, I mean, you know, if this is, I could just imagine a superconductor, right? And I'm just pushing the current, now it's steady, it's just moving, I'm stopped, there's no more force on the system. It's just a steady current. So I did some work to take the charges from zero and move them to a finite velocity. And now they're just flowing around there. At that point, to get them from rest to move at velocity v, I had to do some work. I didn't do the work against resistance, that was futile. What I did was I pushed against the back EMF. And once I'm done, There's a steady current and there's a steady magnetic field.
Would there be a way to relate that to the momentum of like two magnetic dipoles going in different, like, would it be a derivative of the momentum with respect to time, the force?
Well, I mean, there is, at the end of the day, you know, it depends on what the equations of motion on here. In the problem I looked at the beginning, I was saying, oh, there's resistance, there's a battery, that's what did the work, okay? We could also have imagined, you know, we cranked up the voltage at some point. There would be additional work that would have to be done against the drag force that the resistor is there. But I'm separating that. It's not the problem. There's no resistance, there's no battery. I'm just asking the question, if I wanted to somehow get a current loop to go to a certain rate, how much work that I have to do? And the work I have to do is against the back EMF. Yeah?
So it makes sense to me that you put in work to, you know,
To spin up this.
Right. What I'm trying to reconcile is that the location of the energy overall, because you have
Yeah.
down there that it's in the B field.
That's right.
I'm wondering, how, is it first in me
Yep.
and then in the B field?
That's right.
Yes, okay.
That's correct.
Okay.
The mechanical work I did is, the analogy I like to make is, if I need to walk up La Luz Trail to 10,000 feet, I did work. Now, forget about the fact that there's dissipation and I'm hungry, but, you know, I had to drag myself up against the force of I'm walking this way, but gravity's pushing me that way. That's still J dot force, it's the opposite direction. I have to push myself. Now I'm here. I have a lot of potential energy. If I just rolled myself up in a ball, I can roll all the way back down and get all the kinetic energy back. But where did that energy come from? It came from me, but where is it now? It's in the gravitational field. And then the gravitational field pushes me back down. It's exactly the same thing. I want to continue, and we'll have more questions, because otherwise we'll never get anywhere, okay? All right. I understand it's a good path conversation, but the lecture is not just a discussion section, so we need to continue. All right. All right, so where were we? So we have our four field equations. We have del dot E is equal to 4 pi rho. We have del cross E is equal to minus 1 over C dV dt. We have del dot D is 0. And we have del cross P is equal to 4 pi over C K. Okay? And so now, of course, so Maxwell was the person who took the empirical studies that were going on in the early 1800s and tried to make a mathematical formulation of them. It's actually really kind of crazy. I mean, people didn't, of course, what did they know at that time? I mean, the idea of a field was, actually Faraday was the person who invented this idea of a force field and said there's really not action at a distance, there's this local force field, and whatever the field is what's affecting the charges. But no one really took that seriously except Maxwell. And then was trying to figure it out in terms of fluid flow. They knew about fluids and mechanics at the time. And ideas of divergence and curl were really about vortices of flows and sources and sinks, and that was the picture. But then he realized that these equations were inconsistent, right? Because if you look at this equation of motion, and you look at Ampere's law in particular, if I look at the divergence of this, Well, this is zero. Okay, the divergence of a curl, no matter what the field is always zero, which tells me that del dot J is zero. But we know we have the conservation of charge. And the conservation of charge, let's remind ourselves, but we had discussed this a little bit earlier, is that we can think about a general kind of conservation law. So I have charge inside a volume is the integral of the charge density, okay? So I have some volume, whatever volume I have, and I have some charge density inside of it. That's the charge enclosed. The question is this charge conserved or not? Well, if it's the only way that the charge can change, the charge inside this volume can change, is if it's moving, because charge is neither created or destroyed. So this is equal to minus R, where R is the rate of change of Q inside, out of the volume. Okay, so stuff can flow, we can have stuff moving out of this volume, that would decrease the charge. That's why this sign is negative. If we define R as the rate at which charge is leaving the volume, rather than the rate at which it's entering the volume, then we have this minus sign, okay? And this is equal to, we can define J as the flux density or the current density. So that is equal to the surface integral of J dot NdA, where the n hat is the normal out of the surface. Okay? So that's the equation of conservation of charge. It says that the only way the charge can change inside this volume is if it's flowing in or out, not because charge, poof, disappears there or disappears, okay? And to the degree that we have a fixed volume again, so now I'm gonna say the charge is a function of time, because the current density is changing as a function of time, then this equation for some fixed volume is equal to the partial respect to t dq dex, okay? And according to the divergence theorem, the flux through a closed surface is equal to the sum of all the divergences within the volume by the divergence theorem. And thus, we have what's called the continuity equation. Okay? There's continuity in the motion, that's where that comes from. Okay? Or, equivalently, d rho dt plus del dot j is zero. So this continuity equation is equivalent to conservation of charge.
Are you missing a negative sign in your negative equation?
I'm sorry?
Are you missing a negative equation in your?
Yes, thank you. Yeah. Thank you. But that's not consistent with these equations, the proto-Maxwell's equations, because this is only, Ampere's law is only consistent with magnetostatics. Magnetostatics, as you remember, was when we have current but the current is neither diverging or converging anywhere, it's a steady current. So Ampere's law doesn't allow for a current that is changing with time, like this one where I, ramped it up. So, for historical reasons, this is the correction term to this was called the displacement current. Okay, so Maxwell added an additional term to Ampere's law. Said del cross B, there's the conduction current and another term, which we'll just call JD. It doesn't have the same units because of this factor of C or mu naught, but I'll just call it that, because that's what Maxwell did, which is the displacement current. And chose it in such a way that it was consistent with conservation of charge. Because for situations where I don't have a steady current. So again, let's take the divergence of both sides of the equation. The left-hand side is 0, and the right-hand side is this. Okay. But del dot J is equal to minus d rho dt by conservation of charge. Okay? So this tells me that 4 pi over c times d rho dt is equal to the divergence of this displacement current. Okay? But we know that whatever rho is, it's equal to 1 over 4 pi times the local divergence of E, because that's Gauss's law. Okay? Rho tells me what the local divergence is of the field. So now I can replace that and say 1 over c, the divergence of E is equal to the divergence, the E dt, this derivative, is equal to the divergence of K. And thus, what we have from this is that these, to be consistent, this thing must be equal to 1 over c plus some other vector, let's call it, I don't know, v, where the divergence of v is 0. Because this equation doesn't tell us the full solution. I could, in principle, have another term there whose divergence is 0, and that would still satisfy this equation. Okay? Yeah?
Do we generally just set v to whatever is convenient for us?
No, yeah, so I was about to say, at the end of the day, what we have is something that we look at empirically. And empirically, this is 0. So this can't be fully derived just from the self-consistently. In some sense, it's a law of nature that's just the facts map. Okay? Okay, so we just find empirically that that's true. And so what we have is this is the displacement current. And so we put it all together, and what do we got? We have the general Ampere's law. The curl of B is 4 pi over C, J plus 1 over C. Yeah,
What is, even if it's zero empirically, what is V the potential of?
it's nothing. It's just an additional term that could give rise for curling B.
Okay.
There could be something else there, in principle, some other kind of field current that does that, but it doesn't exist.
Okay.
Yeah. Very good. So what we have here is that a changing E creates a curling B. In the same way, the changing B creates a curling E in Faraday's law. So we have now the complete set of Maxwell equations. Yay! A sad story is that Maxwell wasn't really sure about this. Like, this is, he's kind of, you know, the history I've read. He's like, these are the equations I like, I don't really know. They weren't written in this form. It was written in this form about 20 years later by Heaviside. But as we know, the most amazing aspect of this, and I just find this to be the most beautiful thing in physics of all times, and it's the way the scientific method works. I mean, if you just go back and think, how did we get here? There was, you know, there were little pitfalls, and, you know, they were looking at the forces between them. There was Coulomb's law, and, you know, then they put in, literally, this is how they discovered electric current, is that they had frogs' legs, and they put different pieces of metal in these frogs' legs, and they started to jerk around, oh, there's some, you know, current flowing there. And, you know, they started to empirically see stuff and get a set of equations that didn't have this in there. There was a theoretical construct of the field, which was Faraday's genius. But then, just by pure, like, inconsistency of the theory to make itself consistent, this term had to be there, right? And from that, you predict that there are electromagnetic waves that travel at the speed of light. They, you know, they had other constants in here, but the prediction that light was an electromagnetic wave came from this process, and it was a decade after Maxwell died that no, I forgot who did, just the name's Florida, did the experiment that with radio waves that showed that radio waves are electromagnetic waves. Yeah.
That term you circled, that was contributed by Maxwell.
Yeah. Yeah, that was yeah.
They did all this before vector calc was really codified correctly, right?
That's correct.
Because
It was really vector calculus came a little bit later, to my understanding, and it was Heaviside that wrote these equations in this form that we know it.
I think it's pretty amazing to think that vectors as a concept weren't actually around until I think the 1840s.
Yeah.
Like,
Well, it's amazing. I mean, my great-grandfather was born in 1850, okay? I mean, we're connected. And he was, you know, he lived 110, but that's another story. But, you know, we are still part of that history, right? I mean, this is,
It's
my
not
grand
as-
scheme of things, it's kind of amazing.
it's not as
It's
old as it seems sometimes.
Yeah, it is amazing. All right, love it.
I had no idea how high he was.
All right, so, very good. Now, first, a question here. Why didn't we just see this term empirically? I mean, Ampere measured the magnetic fields that were generated by currents. The currents weren't all steady. They had, turn on currents. The currents were changing with time. We had changing electric fields. Why wasn't this seen empirically? Yeah.
1 over c is a really small number.
That's right. And so let's think about the following problem. Let's say that I have, some situation where I'm changing the system as a function of time with some characteristic scale t. So that is to say, there's some rate at which I'm changing things. And I want to see what the sort of the scale of this, right? So there's also some length scale. Over which I'm looking at the system. This could be the size of the system itself, or it could be where I am relative to the system. Okay, so there's some length scale L. Let's just do some dimensional analysis here. Okay, so I could say that the Maxwell Ampere law will say, okay, there's some characteristic derivative here. The curl goes like B over L, right? Goes like J over C plus 1 over C over T times whatever E is, okay? However, we can say, so here's a question, I have, say, a solenoid, and I'm changing the current through this thing in order to create a magnetic field through this thing, through this curling magnetic field. Can I just use Ampere's law and calculate, as we do, the field of a solenoid? Or do I have to take into account the fact that there's a back EMF that's going to arise, that is going to give me another changing flux, right? Because what we have in this situation, we know that the E around this loop, E times L, is on the order of 1 over CT B L squared, okay? So this electric field already is on the order of this, just from dimensional analysis, okay? And so if I look at this, what I see is that B, there's a correction term here. That's been neglected. But what is that correction term? This is small if L over CT is much, much less than 1. We can think about that in many different ways. I can equivalently think that this is neglected, can be neglected if the time scale over which I'm ramping up this current is much, much less than L over C. What is L over C? L over C is the time it takes for light to propagate a distance L. Right? So if the time, the rate at which I'm changing this is tiny, no, that went the other way around. It should be much, much bigger. That makes much sense. The rate is the other way around. In other words, this is effectively instantaneous, right? This equation is this equation. That makes sense. I have to change, if this is a foot, right, it would be a nanosecond. I have to change this thing very fast. And that's, as was just said, as Kristen just said, that's speed of light is so big, that doesn't matter at all for this kind of problem. So they would never see that empirically. However, this also requires whatever L is to be much, much less than C times C. That's, again, it's fine. If I'm changing this thing in microseconds, but this thing is, something small, this distance is going to be much, much smaller than that distance that light goes a long way in that time compared to that. Unless I happen to be far compared to that distance. So if this thing has some characteristic scale L, but I'm over here, and my distance from this thing is big enough compared to that C times T, then I have to worry about that term. And that will be true when I'm in what I will call the far field of electromagnetic radiation. Let me just finish this thought and I'll take a question. So what this is saying is, so let's say this was an AC circuit. I'm oscillating this thing at some frequency omega, so that T is 1 over omega. Then we remember that this is related to the wavelength. How is this related to the wavelength of the radiation? Omega over C is K, and K is 2 pi over lambda. Remember that stuff? Review it, okay? So this goes like the wavelength. So this is saying if I'm close compared to the wavelength of the radiation, I'm in the near field, and in that case, I can ignore the displacement current, and we call that quasi-static. So even though it's not static, I treat it like statics because it's just as if it were the instantaneous value of the current. Because the retardation effects having to do with a finite propagation time are negligible. But if I'm in the far field, then it takes time for the information to get to me, and it's no longer quasi-static, and I need to think about dynamics. Okay. You had a question?
Yeah, I was going to clarify what physical consequence this correction term is for. Is this for the back EMF or conservation of?
No, it's not back EMF. This is not about Faraday's law. This is about an additional term in Ampere's law for the magnetic field.
Which accounts for what physically?
How much magnetic field there actually is there, okay? And I'm saying that this term is a small correction. I can get away with calculating what the magnetic field is right here by just thinking about what the instantaneous current is, letting the current vary as a function of time, even though, because the current is changing as a function of time, there's going to be a change in current that makes a changing magnetic field. And that changing magnetic field will cause a displacement current, because a displacement current is a changing electric field. But I'm saying that I can ignore that and get an excellent approximation to what the B field is by just using Ampere's law without the displacement current.
Okay, so.
But the displacement current will matter if at that time I look in the far field, which would be many wavelengths away from the system associated with the characteristic rate of change, I would have to take that term into account because this would not be small.
So the physical feature which that correction term corrects for is the displacement current?
It just,
Yeah, okay.
and this term is the displacement current, and what it corrects for is what the magnetic field is due to both conduction and displacement current. The magnetic field in this solenoid is not just what we would get from Ampere's law by putting a little contour. That would be not exactly correct. But it would be an awesome approximation when this is small. That's why it wasn't seen when people were looking at induction currents, and they didn't notice what Maxwell found theoretically because this term was a small correction and they would never have been able to measure it. Okay, good. So with this, we can look at the more general. We're going to talk about dynamics, but the first thing we're going to talk about is quasi-statics. So as I say, if these approximations are true, we can do quasi-statics and include these time dependencies without thinking about the fact that the changing currents cause electromagnetic radiation. We will talk about that, but first we'll talk about quasi-statics. To do that, I want to talk about first the general equation of motion of conservation of energy. Okay. So what we said was that minus J dot B was equal to the rate at which energy per unit volume is created in the field, both electric and magnetic. Because plus J dot E is the rate at which fields do work. I mean, on the charges, this is the rate at which charges do work on the field. Okay.
When you say is created in the field, you mean like is put in the field?
That's right.
Right.
Yeah, there was no field to begin with, now there's field. That's why I say the field is created. We had no magnetic field and then we created a magnetic field. All right, so we have now from Maxwell's equations a relation that tells us what J is, because we know that the curl of B is equal to 4 pi over C J plus 1 over C dE dt, which tells us that J is equal to C over 4 pi the curl of B. That's if we just had the usual Ampere's law. But in addition, we have plus 1 over 4 pi d E dt, minus. Right? Just solving that equation. So we can plug that in to this equation, and we're going to get that this is equal to minus C over 4 pi E dot the curl of B plus 1 over 4 pi E dotted into the E dt. Okay. Very good. So what can we say about this? Well, if I look at, let's consider the divergence of the curl of E cross B. Okay. So this is by our Einstein summation rules. The partial I and the ith component of this summed over I, which is equal to epsilon ijk ej dk, which is equal to epsilon ijk partial I on the first guy times B plus epsilon ijk ej partial I dk. Okay. But this is equal to the kth component of del cross B by the usual rules of epsilon ijk. So this is equal to B dot the curl of B. What about this? Well, I'm going to do the old switcheroo, switch J and K and put a minus sign because I'm doing a non-cyclic permutation of epsilon ijk. And this is why. It's the jth component of del cross B. So this is equal to E dotted into the curl of B. Okay? So putting that together, what I have is minus J dot E is equal to what? Well, minus that is equal to this minus that. So this is equal to the divergence of the curl of B minus or plus, I have my C over 4 pi yeah, okay, good. And then I have B dotted into the curl of P. The minus sign. No, this plus 1 over 4 pi e that into the e dt.
Isn't the curl of E1 gonna be minus?
It is. So the curl of E is equal to minus 1 over c dv dt.
No, I mean, with the sign in front of that should. Oh, no.
I think it's right. I think it's right.
Should that say J dot E equals?
Yes, this is, let me get this all, let me put in all the right signs and all the right equals. This is 4 pi over c. I mean, c over 4 pi is equal to minus j dot e is equal to this with a minus sign. And when I put it all together, I get the following. I get that minus j dot e is equal to the divergence of c over 4 pi e cross b plus d by dt e squared plus b squared over 8 pi. Because this is equal to a half and similarly for b. The algebra doesn't matter. The end result is what we want to focus on. What is this equation telling us? Well, this looks like the continuity equation.
Well, has like the potential energy, like the v squared over 8 pi term?
That's right. That's the total energy in the field, the energy density. What this equation is telling us is that du dt plus the divergence of something I'm going to call S is equal to minus j dot e, where u is this and S is this.
Same equation.
So this is conservation of energy. We can contrast that with the equation we had written just a moment ago, which was this, which we said was conservation of charge. How do we interpret the terms in this equation? U is the energy density in the field. Right? So what is S then? In analogy to this. It's the flux of energy. In the same way that J was the flux or the current density, the rate at which charge density is flowing, S, which is known as Poynting's vector. Woo!
Because it points at something.
It points in the
But
direction
it's
of
actually a
propagation.
person, his name was Poynting, he was a Poindexter, it's clear why.
The one time I like when something's named after a person.
Yeah.
Maxwell.
And the Poynting vector is equal to the current density of energy. It's the rate of energy per unit area, such that if I integrate this through a closed surface, that's how much energy flows through that surface. What is this, and why is this 0 on here, but it's not 0 on the right-hand side here?
No source or thing there.
Because there's a source. Electromagnetic energy can be created or destroyed. The total energy is conserved, but the electromagnetic energy can be converted into mechanical energy. So this is the rate at which mechanical energy is converted to electromagnetic energy. Plus that is the other way around. Plus this is the rate at which electromagnetic energy is converted into mechanical energy. That's only heating. That energy in a resistor is going into dissipation. But the minus of that is the rate at which energy is taken from the mechanical motion of the charges and put into electromagnetic energy. So this is a general form of a continuity equation. Yes, someone had a question?
I wanted to comment, it's fun how E cross B points in the direction of the EM wave propagation.
Yeah.
Which makes sense, because that's the direction the energy is going.
Well, that by definition you need, and we'll talk more about that. We'll talk about some other examples where it's a little less obvious that maybe what direction the pointing vector points in. We'll come to that in just a moment. I do want to, let's express this in integral form. So in integral form, I can think about integrating this around in a closed surface. What this is telling me is that if I integrate over a volume here, and use the divergence theorem, says that the electromagnetic energy inside a closed volume can change for two reasons. It can decrease if energy is flowing out of the volume. So if there's a closed volume and energy is flowing out, the total energy in the electromagnetic field will decrease. Is everyone clear what this is? So this represents the flow of E&M energy. The flow out of the volume, okay? And the flow out of the volume will decrease that. That's why there's a minus sign here. And this is if there is some kind of work being done that's creating that energy. That's about the creation of energy through mechanical work done against pushing current against an electric field, like me walking up a Leatherwood trail. Which I haven't done in a long time. Oh, look, a fresh board. All right, very good. So let's look at a simple example, that kind of a couple of quasi-static examples. Let's say I have a conducting piece of material, finite conductivity, and I have current flowing in this thing. we know that I'm constantly putting energy into the system through the battery, but the energy is constantly being dissipated by the resistance, okay? So I want to show that that energy conservation is, so this is a finite conductivity. And there's a current density flowing inside this thing. It has some area A, okay? Some distance between these things. And I want to show that the continuity equation for energy shows how electromagnetic energy is flowing in this system, okay? Let me get my cheat sheet here to make sure I'm doing this right. Come on, wakey, wakey. Okay, very good. Okay, so if there's current flowing inside here, let's just blow up this thing a little bit more. Here's this cylinder, and there's current flowing. So there's a magnetic field, and the magnetic field curls around here, okay? So there's a magnetic field coming out of the board over here, and a magnetic field going into the board over here.
Oh, yes.
Right? So, and now what direction is the electric field pointing in? Is there an electric field in this problem?
There's force, the dependent force.
Yeah, and there's an electric field. And what is that electric field?
It's a wire.
And then what is it equal to?
It's really like voltage.
It is Ohm's law.
Yeah.
And so what is it? So J equals sigma E. So E is J over sigma, right? So there is an electric field. So what direction is the Poynting vector pointing in this case? Let's see, did I get this right? Oh, I got it backwards. Current, magnetic field going into the board here. Put the chalk down, then do your right hand rule. B, okay, good. So now what direction is this? D cross E.
Radially.
means S. Interesting. So S is pointing radially inward in this problem. Let us show that the flux of the energy into this thing has to equal to the energy that's dissipated into this thing. So we can calculate that. So firstly, the magnetic field inside at some radius r is what? Well, we can use Ampere's law to get what the current is at that radius. That was simple. So that's the B at some radius, magnitude that, is equal to twice the current enclosed at that radius over C times R. That's just from the usual Ampere's law, making a closed loop and so forth. That's the simple thing. And the current enclosed is equal to pi r squared times the current density. Right, so this is equal to 2 pi J R over C. That's the magnetic field at that radius. Okay? So what that tells me then is that the Poynting vector, which is C over 4 pi E cross B, is equal to, we got, this is B, this is equal to C, the magnitude of E, the magnitude of B, in the minus, I'll call it S direction. Well, S points radially outward, so it's in the minus S direction. So it's the radial unit vector in in cylindrical coordinates. Okay? So now we can plug that in, and I'm not gonna, so it's minus r over 2 times the magnitude of the current density times j in that direction. Okay, so let's calculate the flux of energy in the whole resistor. Okay, so what I want to calculate is this. But the only place that S is not normal, the caps, it's normal, it's only along the side of the cylinder where this is non-zero. So this is equal to minus S times, let's see, the length of this thing, let's give it a name, let's call this size L. So this is then equal to the perimeter 2 pi times at any radius r times L. That's, so I'm making a little surface inside here at some radius r. The area of that loop is the perimeter times the length times S at that radius, which we have over here. And so this is equal to minus 2 pi RL times R over 2 J times D. Okay, which is equal to pi R squared times J times E. And this is equal, well, we're going to have to L times L. Is the current flowing through this. And what's E times L? That's the voltage across this thing, which is equal to the power dissipated, which you know from freshman physics, or high school physics, or something like that, right? So what this is saying is we have conservation of energy. The energy flowing in from the resistor, due to the battery, is being dissipated through ohmic heating. Okay? So the conservation of energy works in the context of this quasi-static problem. All right? We'll continue this, we'll take a question, and then if there was a question. Yeah.
I was going to ask, but we know the energy is actually coming from the battery.
Yes.
Yeah, but at the same time, we're seeing it's actually flowing radially inward from directions that aren't even the direction of the battery.
That is really interesting. So let me just maybe conclude with one little point. If we're thinking about magnetostatics, this seems crazy. Because exactly as you said, Benny, it looks like the energy should be flowing this direction, but it's saying the energy is coming in radially. And that's really because at the end of the day, all that really matters, the physical property is not S itself, but the divergence of S. That's all that matters, okay? And so it would make much more sense to say, let's take the energy density, instead of I times, so I'm gonna have the current times the voltage. That seems like a much more natural thing. Let's see what that is equal to. Well, that is equal to and this is equal to okay, and in statics, this is 0. Which means that the more natural thing to do in magnetostatics is to choose S like this, because this gives me the right equations of motion if I have the local density. And that's why it's a little bit confusing. S is actually fictitious. What's really important is the divergence of S.
That's the one with physical significance.
That's right. And in magnetostatics, this is really what I should choose. The energy is flowing along the current. That doesn't really matter because they both have the same divergence. Yeah.
You say that S doesn't have any physical significance, but sometimes it does. So, like, because clearly E dot D, or E cross D is useful in a way.
It is, but all we ever measure is not S itself, but its action on something. So I can ask about radiation pressure, for example, right?
Yeah.
Where there's a force that a field will carry. But what really is physically significant there is how much energy flows through a particular surface. And if I have two quantities that give me that same physical measurement, I really don't care. I can't say that S was true. What was really all that was important was the flow of S.
Can we find S everywhere and see where the lines go for like the?
But what do we measure? We don't measure S, we measure the force or the momentum change. Right? What I'm saying, in statics, in the same way that I can make a property, I can make an S that satisfies the same equation of motion. That gives me the right conservation of energy, and that's an equally good formulation of S that's not equal to E cross B. Okay? So physically, all I can measure in this problem, in the statics problem, is how much energy is, of course, when I have radiation, it's another story.
Is the S direction like the same direction as the force?
It is, because we'll see next time it's related to the momentum of the field. So there's a rate at which energy is changed, and there's the rate at which momentum is changed. The rate at which momentum is changed is called force. So the fact that we can change the momentum of matter means that that change in the momentum of matter could come from the fields, and vice versa. The momentum in the fields, in the matter, can be transferred to the momentum in the field. And that direction of momentum is going to be the Poynting vector. But in quasi-statics, I have some flexibility. And it's more natural to think about the energy flowing this way. It gives me the same answer. They're physically equivalent. Yes?
If I take the limit that I took 1 over, basically if I omit the last term of the fourth Maxwell's equation and do the same for, obtain the S exactly and do the same here, do I get these as a dominant term?
No, because in fact, what's actually happening is there's retardation, there's radiation. So if I'm changing current in any way, then I have the change in current causes radiation. So the actual field is actually radiating into it. But that time is instantaneous in this time, that we're not taking that into account. This is a quasi-static situation. In fact, nothing was changing as function. This was steady state. That's why this term was 0 in this problem. There was no change. And we were just looking at the steady state. And we found that this equals this with no change in the energy density at all. That's what we just found. Del that S is right. All right, it's getting late. The next class needs to come in. I'll see you guys next, actually tomorrow. Yeah.
Hey, good luck.